Enga mana, enga reo, enga rau rangatira, onge hoa wha, tēnā koutou katoa. A very warm welcome to you all, our distinguished guests, colleagues, students, friends from our community, and in particular the friends and family here to support one of our newest professors, Robert McKay. My name is Bryony James. I'm the new provost here at Te Herenga Waka, and it's my very great pleasure to be able to introduce Professor McKay, Director of the Antarctic Research Centre and Professor of Geology. An inaugural lecture is a fantastic event where someone who has likely given hundreds of lectures in their career gets to give their first public lecture as a professor, the highest academic rank you can achieve. So it's an opportunity for the whole university community, and I mean the word community in the broadest sense, to come together and celebrate Robert's achievements, and also an opportunity for Robert to share his story and link it back to his friends, family, colleagues and students who have been part of the journey along the way. Professor McKay is a distinguished expert in Antarctic research, with his years of research experience focusing on geological and climate change effects on the Antarctic ice sheet. Robert studied right here at Te Herenga Waka for his bachelor's and master's of science in geology. He then completed a PhD in geology and worked as a research fellow here before taking up the role of lecturer in 2012. The journey from lecturer to professor in 11 years is frankly meteoric and reflects an international reputation for research excellence. This is reinforced by the trove of accolades and awards he has received over the span of his career, including the Prime Minister's McDermott Emerging Scientist Prize, the Prime Minister's Science Prize, and the American Geophysical Union Asahiko Taira Scientific Ocean Drilling Research Prize. That is a lot of swag. He is not a desk researcher, more of an action man, at least an ice man. And as the leader of the International Ocean Discovery Programme, which is one of the largest international research collaborations in earth science, he sailed in 2010 to Wilkes Land in a remote bit of East Antarctica. And in 2018, amongst other trips, he led the $18 million IODP expedition to the Ross Sea in Antarctica to capture past ice sheet and ocean interactions. Our university community benefits greatly from Professor McKay's knowledge and expertise. He is obviously in great demand and highly sought after, and he's been invited to speak and present at numerous events across Aotearoa and the world. So this evening, I'm thrilled to have the opportunity to hear from him, and in tonight's lecture, Professor McKay will present the geological evidence for how Antarctica's ice sheet has responded to a shift in greenhouse gases through geological time. He will explore how this hard-won data has fundamentally altered our understanding of how quickly and extensively ice sheet melting could occur in the future. Please join me in welcoming Professor McKay.
Tēnā koutou katoa. Well, thank you, Bryony. That's it's a lot to live up to there. Yeah, it's a little bit hard to sort of hear all that sort of said about yourself. First of all, thank you all for turning out on Halloween. As you can see, I've dressed for the occasion. Just like to apologise to my two children for missing out on trick-or-treating tonight, so we can make sure we ply them with lots of sweets after the talk. Thank you all to friends and colleagues that have turned out as well tonight. Again, I know that it's hard for some of you to listen to me talking for over almost an hour. Yes, so the title of my talk is How to Melt an Ice Sheet, and this is a little bit of an opposite world to what I normally live in, which is why do we even have ice sheets in the first place? So a lot of my research is actually quite academic focused, just looking at the history of those ice sheets over millions and millions of years. And as this sort of emerging threat of climate change, which has now become emerged, we've actually realised there's quite a bit of relevance to these past climate histories. And the challenge that we have is trying to distill out some of those really long-term processes that occur over geological timescales and thinking about what are the implications over decades to centuries. And they're not always so easy to distill. So I'm going to focus most of this talk on this question: how do we actually melt the ice sheet? So it's a small part of some of the overall suite of research that myself and my students and my colleagues do in the ARC. Now, I come from a pedigree, if you want to call it that, or a whakapapa within the ARC around the specialisation that we've found a global niche for, which is the geological history of that ice sheet through geological drilling. So I've put here my two sort of key mentors, and I haven't shown all my mentors because I couldn't fill up the whole screen. There's a huge suite of people internationally and nationally that have contributed to the research I'm going to show. But here we have Peter Barrett, the inaugural director of Te Puna Pātiatia, the Antarctic Research Centre. Peter will be here tonight. He's just running a little bit late. And for those that know Peter, that is true to form. So he will be here from all accounts. So yeah, it's great that he still keeps us active and on our toes. So Peter really revolutionised this field. He was, in the same year he became director of the Antarctic Research Centre in 1972. He also sailed on that ship there, the Glomar Challenger, built by Howard Hughes. And it was the predecessor of the International Ocean Discovery Program, the deep sea drilling program. And on that expedition, it was the first one down to Antarctica, they discovered the antiquity of the ice sheets went back tens of millions of years rather than the few thousands of years they had thought previously. And so he spent much of his career chasing the holy grail of when did those ice sheets first develop and why. And there's things like changing carbon dioxide in the atmosphere is one component, but there's also those plate tectonic motions that have fundamentally changed the way heat is distributed around the planet. So that led him on a journey to develop these new platforms where we drill through floating ice. And so in some cases it's sea ice, which is only a few metres thick, a lot of technological challenges there. And so within that group we also had Alex Pine, who was developing drilling technologies to really do something that globally no one else was doing. And that culminated in the Inaugural project, which was when I came into my PhD project in the mid-2000s. And that was under the guidance of, here he is here, just talking you up. So that was under the guidance of Professor Tim Naish, who had taken over the mantle from Peter, both as director of the Antarctic Research Centre, but also this technology to drill through, in this case, a floating ice shelf, which was a huge challenge in its own right. And then I became director 4 years ago, and just prior to that, sort of led my own drilling expedition to Antarctica, along with a lot of other help from international colleagues. So that's a bit of my journey here. A lot of the work I do is also, we'll go back, is understanding that connection of the ice sheet to the oceans and the global climate. So we think of Antarctica at the bottom of the world, but that's not the way I think of it. I think of it at the centre of the world. And if you look at it from this perspective, you can see why. It's connecting all the large ocean basins on the planet. And the ocean basins are how heat is distributed globally around the world. So if Antarctica expands, it can potentially restrict that exchange between those ocean basins. If it contracts, we can have better exchange between those ocean basins. And so what happens here is that's regulating heat transfer between the two hemispheres. Now, if you think of that in a New Zealand context, look at us there on the side of the Pacific, the biggest ocean basin, you can imagine that interplay of Antarctica contracting, potentially more of a tropical influence on New Zealand. So those are some of those connections, and a lot of guidance there from Professor Lionel Carter, who was in the office next to me for many years, understanding those connections. But I'm not going to go down that pathway. I'm going to look at the obvious connection that we think of in New Zealand with Antarctica, which is it melts, it rises sea level. And so I put in there for scale the size of the moon, and you can see it's a similar sort of scale to Antarctica. That's how big Antarctica is. And it's 4 kilometres thick in an ice sheet in places. So if that was all to melt, it's 58 metres of sea level rise. So our challenge is going, how much of that is vulnerable to rapid collapse and retreat going forward in the future? Now, there's no way all of that's going to melt with climate change, so don't panic. We think it's all as metres rather than tens of metres. Maybe. So where did this journey really begin? And I saw Matt Patterson come in before, there he is. And this is sort of a changing world as well. This was 1998 as a master's student. 3 students. We had a couple of weeks with Peter Barrett and a Dutch researcher up in the mountains, a professor. But 3 students, never been to the ice before, dumped up in the mountains, left the camp and explore and map. It was fantastic. It was a real journey of discovery, both personally as well as scientifically. And it's something that, everyone that's been down there as a student sort of takes this as one of the sort of changing points in their lives. We hear that time and time again from our alumni. So it's always been a sort of trying to, carry this forward, pay this forward, take students down with us. We're still taking students down with us every year, and a lot of the work I'm going to show is actually being led by students within our group. So I really want to emphasise that we give leadership roles to students and they flourish. Now the reason I started that journey there was because I also wanted to say, what do we know about the Antarctic ice sheet at this point in time in 1998? And there was this very divisive argument. It's called the Sirius Group debate. I'm not going to mention the Sirius Group anymore. But it went from this idea that there was one pool of researchers who said that ice sheet has been stable, hasn't changed for 14 million years. The dry valleys have been dried, it hasn't rained, it's a polar desert, there's been no melt. And there was another group of researchers that had a different line of evidence that said, actually, we think there's been collapse of what we call the marine-based sectors of all of Antarctica. And by marine-based, this is where the ice sheet is sitting on the Earth's surface below sea level. And the important aspect there is it's connected, it's touching the ocean. And we all know if we put an ice cube in a glass of water, it's going to melt a lot quicker than it will if you just sit it leaving on a bench. So the ocean carries a lot of heat, and heat is what melts an ice sheet. So this was a very divisive argument. We actually, Peter was my master supervisor, we actually were leaning towards that stable side at that point. We thought the evidence was stronger. We thought the dynamic argument was a little bit flawed in some of its arguments. And we still, maybe they were right for the wrong reasons. So that's something we were always kept in the back of our minds. So we'll park that, but that's where we were over 20 years ago. So let's get to the key question. How do you actually melt an ice sheet? Let's go mad scientist now. And for Greenland, it's actually relatively straightforward, relatively. You turn up CO2, you turn up the way that the Earth is absorbing heat in the atmosphere, and you're melting it from the top down. So we can measure surface melt in Greenland. We can actually see it. There's a river on the surface of that ice sheet. And that water percolates down to the base of that ice sheet, and it creates a slippery bed. So that ice sheet starts to slide faster. It's kind of like putting oil on a fry pan. It moves around. So it slides faster into the ocean, and it melts. And because it slides, it's also like deflating a balloon. The ice sheet sinks, and so it goes into a warmer air mass, and so you get this positive sort of feedback loop where the ice sheet continually melts. And so we can actually measure that. We think the melt going forward in Greenland is going to be pretty linear through time. So that's projected, that's built in pretty nicely into IPCC, the Intergovernmental Panel on Climate Change's assessments on future climate change. The Antarctica is a little bit different. So here we have rising CO2, and over 20 years it's increased by about 50 parts per million. And this is the mass balance of the ice sheet in Antarctica. So mass balance is whether or not it's gaining more mass through snowfall versus what's been melted on ice shelves and carving of icebergs. So it was sitting relatively stable in the early part of the century, but then you can see it's rapidly accelerating. And you can see the areas here where it's going red to yellow. That's where the ice sheet's melting. So there's a couple of observations you can do here. You can go, well, where is it melting? And it's melting in the areas where there's none of these fringing grey zones. And these are what we call the ice shelves. These are the floating component of the ice sheet. So it's melting where those ice shelves are not there. And I'll talk about why that's important in the next slide. Now, where there's no ice shelves, and it's sitting on the Earth's surface below sea level, those are the areas where it's melting. So even in here, this is the weak underbelly or the Doomsday Glacier region of West Antarctica that's been in the media a lot. But there's also areas in East Antarctica where it's melting, so losing mass. The Aurora subglacial basin and Wilkes Land subglacial basin. So this is West Antarctica, mostly below sea level. And if that was to melt, it's about 3 metres of sea level rise. If all of the marine-based ice in Antarctica was to melt, it's 19 metres of sea level rise. That was that argument about a dynamic ice sheet. Did all 19 metres of that go as recently as 3 million years ago? And for a geologist, 3 million years is quite recent. Now I put CO2 in there and you go, okay, there's almost a quasi-linear relationship there between CO2 and that ice sheet acceleration. We don't think that's the case. There's a bit of a lag here. The CO2 is warming the atmosphere, that gets into the ocean, and the oceans are carrying heat to the ice sheet. But there's a bit of a time delay. So there's a lot of built-in warming that we're worried about. We could turn off CO2 and still that heat is going to be going up next to that ice sheet. So let's talk about that. It looks catastrophic when you put those big red values in there. There's not a lot of sea level rise in there. At the moment, it's a relatively small amount of retreat. But this is the Larsen ice shelf breakup in the early 2000s. And what happened here was, this is quite a northern part of the Antarctic Peninsula region, and it got above zero in summer. So there was a surface meltwater on the ice shelf. And what that did was it filled up crevasses in that ice shelf. And water is denser than ice, so it sinks, and it pushes those crevasses apart. And this ice shelf exploded like a set of dominoes over a space of a few weeks. Now, this is a poster child for climate change. A lot of you have probably seen this. But what this did, it didn't raise sea level in its own right. That ice shelf is floating. But the glaciers on land are sliding into that ocean. That ice shelf, as they come into the ocean, the ice starts to spread. And as it spreads into these embayments, it hits the walls of the embayments and it latches onto it. And it holds on. So it creates this buttressing effect. It sits there and holds back the glaciers from sliding into the ocean behind it. If you remove that buttress, that ice shelf, those glaciers speed up. And in this case, they speed up by an order of magnitude. So a 10-fold increase. So that's one way we can greatly accelerate that ice sheet melt. The other one, there's two I want you to remember for this talk, ice shelf buttressing. The second one is this thing called MISI. It's an acronym we use. It's become common in our world. It means marine ice sheet instability. And this is a very specific process whereby these ice sheets are not just sitting below sea level, but the bed of that glacier gets deeper and deeper as it goes inland, several kilometres below sea level as you go inland. Now, they're currently sitting on highs on the seafloor, so these little ridges. We get a little bit of warming and we trigger a retreat off that ridge. What happens is you expose more and more of that ice to the ocean, more and more of that to that heat. So it's not being offset by increased snowfall. You're getting more melting at that ice front, not being offset by accumulation, and it gets deeper and deeper, so it becomes runaway and it accelerates. And it runs away so much you can even turn off that heat supply and it'll keep going. So it's quite simple physics there. That's our big concern. Have we triggered that retreat already? Some people have argued we've already triggered it in that Doomsday Glacier region I showed earlier, that big red spot. Still debatable, but some people argue there is compelling evidence for that. So where do I come in? Where do we come in with drilling? And so this is where I came in with the Anaugural project, so I had quite a few years off between there and the Masters project. And we decided to drill under that ice shelf. Well, I didn't. Tim Naish did, and Ross Powell. Peter Barrett gave me a phone call when I was living in London and said, "Do you want to come and drill under an ice sheet?" I said, "Sure, that sounds like fun." And it was. It was a remarkable project. This was a world first. No one had ever done this before. Can't believe how lucky I was looking back on this. It seemed to take it for granted at the time. And Alex Pine here has been a stalwart for this. You can see him here, looking particularly happy as always, along with the crew from Webster's Drilling, who have been long-term partners for us in the Antarctic Centre. And they developed this method where they could drill through an ice shelf. They would drill through using a hot water drill hole. They would just drill, blast the ice away. They weren't capturing that. Lower a pipe to the seafloor and collect 1.3 kilometres of sediment from the seafloor in almost a kilometre of water depth and almost 90 metres of ice shelf. Now, there's some technical challenges. That ice shelf is flowing. Remember how I said it's flowing? It's going at 0.5 metre per day, so you get a big bend in your drill pipe and you're trying to bring up 6 metre bits of core at a time. You only get a couple of months to do that. So it's a huge achievement. Looks simple on paper. Again, that was a massive project. And just pointing out Ross Powell, the other co-chief, again, a Victoria University graduate who's gone on to do amazing things globally. So we export our knowledge globally as well. So what did I do for the PhD? Well, I was a sedimentologist, and sediments document what type of environment they've been laid down with. And on a continental shelf in Antarctica, it's quite simple. Not as simple as this, but there's some details, devil's in the details. But under a big ice sheet, if there's a bigger ice sheet than present, they override that drill site. It's going to be carrying gravel, sand and mud. It's like a bulldozer. It just picks everything up, puts it at the drill site. Now, in its current situation, there's very weak currents under that ice shelf, and so it's carrying muds in suspension. It just gently deposits this drape in mud. And every now and then there'll be a pebble in that floating ice and it'll drop out and impact into the seafloor. And that's called ice rafted debris. Now, when we have no ice shelf, we end up with these yellow deposits, and these are things called diatom oozes. This is plankton that's living in the ocean surface. It dies, it settles to the seafloor, and its shells are preserved. These are siliceous shells. Photosynthesising, a really important part of the global biological system and carbon cycle. So as a sedimentologist, I get the colours, the colouring pencils out, and I draw colours of what the core looks like to simplify it down. And each of these colours I'm going to say is a depositional environment, where we have a big ice shelf, big ice sheet, an ice shelf over the site, so we're drilling in this region of the Ross Ice Shelf here. And then when we have these yellow deposits, we can infer there's a collapse of that ice sheet behind it. And this is because of that buttressing effect of the ice shelf. So at the same time we drilled Anaugural, ice sheet modellers were starting to develop this understanding of the physics of when it goes from an ice sheet on land, where it's sort of tumbling down off land in a vertical way, versus spreading ice shelves. That was quite a complex problem for them to solve. And they showed that, yes, you lose that ice shelf, you do indeed lose that buttressing effect and that marine base ice behind it. So that's how we expand our results out to a continental scale. It's not perfect, but it's the best we can do at the moment. I'll show you some ways that we're going to test that further. Now look at this ice sheet model. There's not much happening in East Antarctica. Keep that in the back of your heads. I'm going to segue a little bit into what we did in 2018 with the IADP expedition that I co-led with Laura DeSantis here from Italy. And one of the great things about working internationally on these international projects is you're working with people from diverse cultures and age groups as well. So there's students there from all around the world, as well as senior professors. And so here we spent a lot of time trying to work out how to drill in the outer Ross Sea. Usually there's sea ice, but then there was a catastrophic drop in sea ice the year we went down. So we paid $500,000 US for an icebreaker to support us into that region, and we didn't need it because the sea ice had gone due to climate change. So one positive for me for climate change, but that's pretty selfish. But what we were trying to do here was not look at the physical footprint of ice sheets, but we're trying to understand what the triggers were for triggering that collapse, that initial retreat off the outer continental shelves of Antarctica, the shallow water, 500 to 1,000 metre water depth, before you go into 4 kilometres in the offshore. And so these arrows, these are the long slope currents in Antarctica, and these are wind driven. The winds around Antarctica push the water around that circular continent, and it's like a giant centrifuge. So centrifuges push waters north, and that's replaced by water that's upwelling from depth. And this water at depth is actually a couple of degrees warmer than the surface waters. That's what we think is triggering that initial retreat. And then these other feedbacks, the ice shelf buttressing, marine ice sheet instability, kick in and take over. So here we're just trying to understand that response. Could we see triggers for that initial retreat, as well as you change the amount of ice on the continental shelves, you may be changing how much Antarctic bottom water is forming. This is the dense salty water at the bottom of the ocean that stores a lot of heat and it stores a lot of carbon dioxide. So again, there might be natural cycles once we start to retreat an ice sheet that could change that whole natural carbon cycle. So we drill to test this, up to 4 kilometres water depth on these ships, and you can see it's a big string of spaghetti. We lower that down 20 metres at a time on these huge drill ships. We get to the sea floor, and this here is firing a piston core. So this is a huge pipe that's 830 metres long here. It's got a cod cone drill bit on it, and we fired a piston core down it. So what we've done here is we've got a tube of metal, it's hollow. We've fired pressure down over drilling fluid. It's popped a couple of pressure release pins and fires out 9.5 metres into the sediment. We then take this big heavy duty drill bit and drill over that 9.5 metre hole, pull the core up to the surface, lower another core down, fire another one, 9.5 metres, drill down over the top of that. And we do that repeatedly until we get several hundred metres below seafloor. And we recover drill cores, lots of it, up to 5 kilometres on some of these expeditions. And so we have a drill ship full of scientists, about 30 to 40 of us on there. We get the cores to the surface, we cut them in half, we describe them. So you can see muds here with gravel. And here's Molly Patterson, a former student, Lara. We have paleontologists, Dave Harwood, the person that came up with the original dynamic retreat of the ice sheet hypothesis. Real-time age models. We're understanding what age those sediments are within a few hours of them coming to the core surface. We have instruments to measure the magnetic field of the cores when they're put down. So that gives us an idea of age models as well. So we can tell exactly what time period we're in, and that really guides where we're going to drill the next site, pretty much. And so this is what we're trying to do. We're trying to go back in time, tens of millions of years potentially, into climates where CO2 has been higher than present and where temperature has been higher than present. And so we can choose little snapshots. We can choose our sort of natural climate experiments to see how did the Earth system respond. And so 50 million years ago, we had carbon dioxide over 1,000 parts per million. And this is from global records in the deep ocean. So these are records I haven't produced. And it's the summary in the IPCC assessment report in 2023, 22. And you can see it's 1,000 parts per million in this, and higher 50 million years ago. And this is called the Eocene time period, so we're going to look a little bit at that. Now, the Eocene was very different. We still had Gondwana land was still breaking up. We had sea waves through the Mediterranean and the like. So it was a very different tectonic setting, and we actually probably had no ice sheets on the planet to begin with. So we've got a different starting condition. So it's not a perfect analogue for the future. We can go into 400 to 450 part per million worlds, 20 million years ago, and as recently as 3 million years ago. That was the last time we think we went over 400 parts per million CO2. We're currently at about 420. And then for the last million years, we've been sitting below 280 parts per million. We've been fluctuating the natural ice age cycles from 180 to 280 parts per million. So we'll look at that. Now, the context here is when we go into the IPCC future scenarios, this is changing the timescales from millions and thousands of years to hundreds of years. And so by various emission scenarios, depending on which pathway we choose to take, and I'm just going to say the numbers, 2.6 is a number where basically we're meeting the Paris Climate Agreement. We're limiting global warming to below 2 degrees, preferably 1.5 degrees above pre-industrial. 4.5 is exceeding the Paris climate target about 3 degrees Celsius. So with this scenario, we get CO2 up over 400 parts, 450 parts per million, and then we bring it back down. So it's called an overshoot scenario. This one we stabilise it at 500. And this is the 8.5. Now, some people call this business as usual. It's actually the continuing emissions unabated. I don't think we're going to be able to do that, to be honest. I don't think there's enough fossil fuels to actually do that, and I think we will adapt. But it gives you that end member. So don't panic when you see 8.5, but it does say if we don't change our behaviour or there are natural feedbacks in the climate system we don't expect, we should still be considering it. And we can run models out. And you can show models that are getting similar temperatures to what we see in the Eocene in these scenarios. But do remember that some parts of the Earth system take millennia to catch up to that climate warming. So you probably can't melt all of the East Antarctic ice sheet in 100 years, even though the temperatures are the same. So at the end of the last ice age, these are some of the climate experiments. So 20,000 years ago, we had a big ice age. CO2 was 180 parts per million, and then it rose to 280. So here we had big ice sheets in the northern hemisphere. So below 280, we grow big ice sheets in the northern hemisphere, and sea levels were 120 metres, 130 metres below present. And over 12 to 13,000 years, they rose by 120 and 130,000 metres. So that gives you a metre per century of sea level rise as a standard rate of retreat for a glacier to deglaciate, even with only 100 parts per million CO2 rise. And we've done 50 parts per million just in the last 20 years. 25 years. So it's quite dramatic, but that's an average. The most accelerated retreats were 4 metres per century. We had little pulses where it just went crazy. And so we haven't dealt with those levels of change, right? We started to get civilizations, we developed agriculture because we could predict our weather. Right? So we've been very stable, relatively. We've had some warm periods, but nowhere near as dramatic as a 4 to 6 degree global warming. So did Antarctica contribute to that massive pulse of meltwater pulse 1A 14,000 years ago? And this is a model from Nick Golich, it's not my work, but he was forcing this ice sheet model with ocean temperatures offshore from other paleoclimate records, drill core data that was collected globally. And he showed there was a big pulse 14,000 years ago. And the same time he published that, a researcher in Germany had an ice rafted debris record offshore of the South Atlantic showing pulses, armadas of icebergs occurring at that same time. So this ice sheet was purging itself of icebergs en masse. So he showed, yes, there was a contribution to that meltwater pulse. So I was in the office next to Nick and I said, great model, Nick, it really is. It's a fantastic contribution. But your ice sheet seems to be going too quickly. Once you've triggered that retreat, it runs away what I think is too quick, because we had drilled here, done a short sediment core actually, preparing for drilling. My master's student, Sana Mas, had some datable material in that core and showed that the grounding line, these muddy deposits, very close to that ice sheet margin, retreated Ross Island 8,500 years ago. So it was coming past in its model here 10 to 11,000 years ago. So it was going too quick. So I said, are your physics wrong? He said, probably not the physics of the ice sheet, but he had some feedback that he hadn't considered using the right value for the viscosity of the Earth's mantle. And that sounds weird to go, how on earth does this liquid layer beneath the Earth's crust affect ice sheet dynamics? And this is important because East Antarctica is a big, old, cratonic continent. It's drifted from Australia. It's basically Australia to the south. It's just drifted apart from Australia. Whereas here, this is actually a big volcanic rift system. So it's a breakup of Gondwana, but it's been going active over 100 million years. And so under this more thinner continental crust and active rifting processes, the mantle has a lower viscosity. It means it's more fluid. And so because you've got the solid crust on top of a fluid inner mantle, the ice sheet loads up and it pushes down on the Earth's crust and it sits down and creates this depression. And this is that over-deepened aspect of West Antarctica. Now, if that mantle viscosity is lower, it's more fluid, it pushes the Earth up quicker. And so what this is doing is it's creating less of that marine ice sheet effect. Right? So as that ice sheet is retreating, the slope is not as steep, so it's not exposing as much of that ocean to the ice sheet. So he ran it with a different value, saying most of the ice loss was in West Antarctica, let's use that value, and we managed to match the two data sets quite nicely. So we could still explain all that geological data, but it calibrated his ice sheet model. So we know that ice sheet's model's not responding too quickly going forward in the future. So that's one example of using paleo to calibrate an ice sheet model. Now, I said it's been quite stable over the last 8,000 years. One of the other cores we looked at was offshore of this part of East Antarctica. And this is a remarkable core. It was 180 metres long, but it only measured 12,000 years of time, which is quite a unique record in Antarctica. Each of these are summer and winter layers. So we could look at the changing biological productivity offshore of Antarctica at seasonal timescales for the last 12,000 years. And what we noticed was there was a very strong response to sea ice concentrations, biological productivity to El Nino processes. So we could actually see the response of that. But there was also a baseline shift in sea ice production about 4,500 years ago. So we went into this warm period, but then it suddenly got cold. So the warming triggered a cold period. And we realised a lot of our signals, we actually had a meltwater proxy. We could see, looking at isotopes of hydrogen, which is a component of water, we could see what was freshwater and seawater, and we could see these pulses of freshwater coming out up until 4,500 years ago, and then it stopped, just when the sea ice kicked in. So meltwater wasn't causing the sea ice increase. What it was doing was we had an ice cliff. We had a big what we call the ice shelf calving line and grounding line. We're pretty close together. And then as it deglaciated, we had this huge amount of meltwater input, but it didn't create a huge sea level rise because it was already displacing seawater. And then we had a base of an ice shelf floating on the ocean that was the size of France. And so what's happening is the water's going under here, we get a little bit of melt at the grounding line, but then it refreezes back on. All that heat from that water has been exhausted, and then it gets super cooled. It goes to minus 2 degrees Celsius and comes back out super cooled, and it developed a sea ice factory. So this is another aspect that's really missing in ice sheet models today, is that what we call ocean-ice interactions. How do the ice sheets talk to the ocean? And are there feedbacks in there that could either amplify or dampen future climate change? So here we think this retreat actually caused a cooling, which is why we had a warm period in the mid-Holocene and then it went cold. So counterintuitive. Now you go, is this going to save us in the future? And possibly if the rates of retreat are slow enough, but if we lose that ice shelf, this cooling feedback turns off and it gets enhanced even further, the warming. So this is possibly the biggest uncertainty in ice sheet models, and a whole community are working on trying to figure this one out, including people in our group. The Pliocene time period. This was really where a lot of my focus was on early on in my career. Pliocene is a time period, a geological epoch, 5.3 to 2.6 million years ago, and is the last time CO2 was at 400 parts per million in the atmosphere. And that resulted in a 2 to 3 degree global warming. So we're going to use that same sediment mapping technique. Now we're just going to go to those colours. That's why I showed the colours earlier. I just want you to look at green here. Oh, sorry, yellow. Colourblind, sorry. So the yellow is a retreat event. And we have natural ice age cycles. We know what caused those. Those are changes in the Earth's orbit, regulates how much energy the poles receive. So that's been one interest. But we're really interested in what was the last time that ice sheet collapsed? What was the physical evidence for that? And so we're at this place where there's the blue dot, and we see loss of the Ross ice shelf and collapse of the marine-based ice sheet behind it whenever we see these yellow deposits that I'm going to draw on our drill column. So we call this a stratigraphic log, and this is the only one I'll show. This is 150 to 500 metres below the seafloor in the Ross Sea. When we hit, the deeper down you go, the further back in time you go, the sediments stack up on top of one another. And you can see lots of those yellow intervals. We had lots of ice sheet collapse events. Now, because they were plankton and they got shells, we can actually look at what types of shells they were and where they lived today in the ocean. And some of these shells lived north of the polar front, where there's no summer sea ice. That told us there was temperatures 3 to 4 degrees warmer in the Ross Sea that time that ice sheet collapsed. So Andrew gave us not only ice sheet collapse events, it gave us also the temperature threshold for it. We pioneered the use of lipids. These are the remains of single-cell organisms that live in the ocean. And you can take compounds out of them. You can measure them on mass spectrometers, and you can see the relative abundance of certain compounds and make a direct correlation to temperature for that. So that's really cutting edge. It was still big uncertainties at the time, but we're starting to resolve them, and Bella Duncan did her PhD on trying to resolve some of those. So these are the organic remains that don't have hard shell preservation. So combined, these diatoms and molecular fossils showed us, even in some of the later events, the waters were only 1 to 2 degrees warmer to trigger that retreat. Now, that doesn't have to be a uniform warming. That can just be pushing more heat up from a change in ocean currents. So that's one of our concerns. It's not necessarily going to be just a uniform top-down warming. So Andrew, loss of West Antarctica, that was 3 metres of sea level rise out of that. I said there's 19 metres total of marine-based ice. And so in 2010, for my postdoc, I went down with this great group of people, many of whom I still work with very closely, and we had to travel some pretty rough material. That was a rough cruise. That was 20-metre waves at times, some of the worst storms that ship had been through. But we were offshore of the Wilkesland subglacial basin, which is one of the largest ones. And this is the area that had been proposed to deglaciate in those early studies in '98. And we're offshore here at this site here. So here we are. So we can't do the same thing as Andrew. We're on a drill ship, so we can't go under the ice sheet and see if there was presence or absence. We had to do something different. And so we can do two things. We can look at these pebbles and muds, and these pebbles have been, in the deep ocean it's mostly mud. You go away from the ice sheets, it's always mud, or fossils. Here we've got muds with big gravel, and this is icebergs passing at the site, dumping out material as they melt. And so we can see, when we see these armadas of icebergs breaking out when we have a catastrophic collapse of that ice sheet, so we can see pulses of them. And they were very regular throughout this core. So my PhD student, Molly Patterson, worked on that, and then a colleague from London was looking at where the mud was coming from. And so the glaciers are most erosive at their margin. That's where they erode the most material. And they erode rock, and they grind it into mud. You can see it pulsing out of the front of this glacier. So where that ice sheet margin is, you'll be able to tell where the sediments come from. You should be able to tell where that margin was. So Tina, here we go. So here's the removing that ice sheet. That's the bedrock under Antarctica, right? So it's marine-based in this sector of Wilkesland. And Tina Vanderford, and I put her name up here because she's going to be the 2023 ST Lee lecturer in a month's time. She's also going to be the co-chief of our Space 2C drilling that we'll be doing this year, our new drilling project. And she came up with this novel method to look at the mud, while Molly was looking at these ice rafted debris events in her PhD. And she's also going to be a co-chief on that project, so we're again passing the mantle to the next generation. And so what we noticed was there was these armadas of icebergs, and then the mud source changed. It went from granite source, which are the coastal areas of the bedrock under that ice sheet, to a Farrar dolerite, which is a dolerite is a different type of plutonic rock, so a volcanic rock that's formed under rather than erupting, it's formed within the earth. So we could see huge armadas of icebergs and then a shift to this source of these Farrar dolerites. So that meant we had an ice sheet margin that was well and truly inland by about 100 kilometres. So combined with Andrew and Wilkesland, we fundamentally changed the view of what that ice sheet looked like. We really verified that it was a dynamic ice sheet. It did melt 3 million years ago. In fact, from that provenance work, the Farrar dolerite work, as recently as 400,000 years ago when it was actually less than a 2-degree warming. And that's quite concerning. We didn't quite know how much sea level. Right? We could tell where it was, but it didn't really give us magnitude of change. So we went into the Wanganui Basin. See, Gary Wilson here did his PhD in the Wanganui Basin. We continued on. Molly Patterson said, I want to go back and see if I can see these events. So she did a bit of reconnaissance work, Juliet Sefton in her Masters, and then Georgia Grant did her PhD on a drilling project there, published this paper in Nature showing at the same time we were seeing these collapse events in Antarctica, We had no northern hemisphere ice sheets to worry about then. We had 20 to 30 metre sea level changes. So that was loss of all marine-based ice in Antarctica and Greenland. Now, I said that may have collapsed 400,000 years ago. This is what we're doing this year with the SWACE 2C project. This is a lighter weight drill rig. Darcy Mandano's in the room, is frantically trying to get the equipment down to Antarctica. Really novel technology. Richard Levy, who will be given his inaugural next year, will be the co-chief on that with Tina in the first season. So no doubt he will report back on that next year. So keep an eye on that. That's our next great adventure, trying to see if the heart of West Antarctica went in a less than 2 degree warming world. So how does this relate to ice sheets? And, well, this is what ice sheet models do. They looked at this data and said, we can't recreate that. This is what we get when we force our ice sheet models under extreme scenarios of the Pliocene. We can't get rid of that ice sheet in Wilkesland. And so Rob DeConto, a modeller in America, added new physics into his ice sheet. He added this thing called the Mickey. Right? That's what Nick Gollage likes to call it, because he wonders if they're taking the Mickey with it, because it's a bit controversial. But he's saying that ice sheet can't sustain a cliff greater than 200 metres. It collapses under its own weight. And we see this in Greenland. The big controversy is, does that scale up to a continent? I'm kind of inclined to believe that this is a possibility. And IPCC were as well. They said 2 metres of global sea level rise by 2100 cannot be ruled out if these processes kick in. That's in the IPCC. That's these dotted lines. And it says low confidence, not low confidence because we think it's a low probability. It's low confidence in our understanding of those processes. We need to learn more about those processes. Now, Nick says you can do this even without adding new physics. You can just change the way that heat is transferred into that ice sheet. So he's doing it. Gives you a slightly lower rate of retreat, but it still gets us above what the IPCC give as our range of less than a metre of sea level rise by the end of the century. So let's get a little bit more academic. Let's look at a time period when we've lost all our marine-based ice and we go to loss of terrestrial ice potentially. And so with our drilling in 2018, we went to look at the Miocene climate optimum. This is the warmest climate since we've had ice sheets on the planet. And it was a time period where we saw a very rapid jump in CO2 from 280 parts per million, which is the present interglacial prior to the Industrial Revolution, to 800 parts per million very rapidly. We think that was probably driven by a massive volcanic eruption event in America. It was a 5 degree global warming, quite sustained, and a 60 metre sea level rise. So one argument was, the sea level record came out from an American group, very similar to what we did in Wanganui Basin, who said it was a 60 metre sea level change across that event. So loss of all ice in Antarctica with 800 parts per million CO2. Now models can't do that. They can't melt an ice sheet at 840 parts per million. We drilled out here and we said, well, there's no ice after debris. There doesn't appear to be any icebergs in this region, so no glaciers at the coastline at the very least. We had diatoms, so again we could get temperature. We had those lipids. We could look at the shells and actually measure what the bottom water was. It was 3 to 8 degree temperatures in the bottom waters of Antarctica rather than -2. And those shells also told us it was actually much shallower water for some reason. So the glaciers hadn't eroded West Antarctica as deep as it is today. So it didn't have marine ice sheet instability back then. It was actually inland, mostly above land. It was mountains. So this solves a little bit of a problem for us. We're drilling up in the mountains as well. Freeze Hill's work here that Bella Duncan and Richard Levy have worked on. Chris Krause is a master's student working on some of the stuff as well. They saw there were presence of glaciers in the mountains, so there were some ice around. And so the ice sheet models showed us, at 840 it looks like that, about 20 metres of ice left on the continent. And Bella's work showed temperature and CO2 seemed to be in sync. Throughout 55 million years of Earth's history, they were in sync in the Ross Sea. Temperature went up, down when CO2 went down, but ice volume didn't. Ice volume seemed to be bigger when it was 280 parts per million than it was today. And the reason is, West Antarctica was all mountainous. It was a terrestrial West Antarctica. So glaciers erode below sea level over millions of years. So it went from a kilometre above sea level in places to several kilometres below sea level. And the continental shelves had only a couple hundred metres water depth as well. So that meant you could get a big terrestrial ice sheet growing in a relatively warm climate and dipping its toes in the water. It wasn't susceptible to marine ice sheet collapse. So the work we did in the IDP expedition was we could map again using those same provenance sediment mapping techniques, but during a glacial period, to show we had a big erosion source coming out of West Antarctica at that time period, and we had ice sheets that were 80 metres sea level equivalent in what was a pre-industrial climate. So that gave us some confidence that actually ice sheets do respond to CO2 very strongly. It just had a different geological context to explain that ice falling difference. It also gave us the confidence that ice sheet models were behaving properly. We were quite concerned that they weren't melting all that ice, right? Because they say, well, actually, they've been undersensitive to climate change. That would be a bad thing. They seem to be behaving well in those warm climates. So last one, really quickly, the Eocene time period, 50 million years ago. This is getting really academic now, 1,000 parts per million. Hopefully we'll never get to that. If we do, we definitely are doing a mad science experiment. Now, this was less of an interest to me, but I was on board the ship when it happened. The paleontologist, the person who looked at pollen grains, there used to be vegetation on Antarctica. He looked down the microscope and just went, there's baobab trees in this record, there's palm trees, it's 21 degrees in summer in this area. Bella and Richard Levy worked on these things called glacial erratics. These are big boulders that have been plucked up from the seafloor and brought to the surface by glaciers in recent ice ages, but it's picking up sediment 50 million years old, doing our drilling job for us. So she mapped those in her PhD and her postdoc, showing again these similar temperatures. Now the reason this is important, we think it's lost all the ice at that point, so 1,000 parts per million we do lose the ice, but climate models need to get up well over 2,000 to even 4,000 parts per million to get those temperatures. So one of the big debates you'll hear is, what do clouds do? Do they actually cool climate? Do they reflect more light back into space because they're big, white and fluffy? Or is it water vapour, which is a more potent greenhouse gas? And we think water vapour seems to be a more dominant control in amplifying that climate change response to warming. Yeah, there are the palm trees. So that's warmer than Wellington, right? Not a good thing. So what does this mean for future sea level rise? Well, I think the most obvious one is that 400 parts per million does appear to be a long-term threshold for marine base ice sheet loss. The question is, how quickly do we get to that marine base loss? Can we starve it off for as long as possible? And what I would argue is we need to prevent the loss of ice shelves. That's the fundamental thing. If we lose that Ross ice shelf, these processes, these fast-acting processes could kick in. So the more we can slow the rates of retreat, the more some of those natural processes, like that rebound of the Earth following that ice age removal, that's a very slow process over hundreds of thousands of years. If we melt that ice sheet quickly, it's not quick enough, that response, to slow down the rates of retreats. But over 1,000 years, it will be. So the more we can do that, the more we can help reduce that marine ice sheet instability. And the key to do that is reducing emissions as much as possible, even if we exceed the Paris climate target. So I'm not going to talk about what this means for New Zealand, because that would be stealing Richard Levy's thunder. And Richard he's not here tonight because he's having a bit of a holiday before he goes down to Antarctica for a few months. He leads the New Zealand Sea Rise program with Tim Naish, which was understanding how these projections of sea level rise are superimposed on the variable uplift and subsidence in New Zealand due to tectonic processes, so the vertical land movement. And there's this great mapping tool online on the New Zealand Sea Rise website that shows a 2-kilometre grid of what might be happening anywhere around that continent, around our country, sorry. So he'll talk about that in detail, the specifics about what this means for us in the future. Now, the other half of my role is managing this group of people, director. They make my job pretty easy because we have a whole bunch of leaders in that group, exceptional bunch of researchers, a good mix of international people that have come in, as well as growing our own early career research is something that I certainly got the emphasis, the importance of that from Peter and Tim. So thank you there. I just want to thank some of our national colleagues, in particular GNS Science, who have been a huge collaborator with us over many years, developing these drilling projects with us in sync. My Australian colleagues who I work with closely on IADP, and our international colleagues. We can't do this as a single nation. We work intensively with America, Korea, Japan, Italy, and the like. And again, of course, also Antarctica, New Zealand, for allowing us to get down to the ice and being great at facilitating all this logistics. And finally, just thank you, my family. They can see they're hiding their heads there. You know, long times away from home, obviously, not just for drilling, but also organising these international projects. You see, my kids are not too happy about this. I think they've got every right not to be happy about what we're potentially leaving them, to be honest. But we do. I want to finish on a positive note, and I've intentionally put up this controversial model just to annoy Nick Gollage, who's already walked off in disgust. He had to catch a train to wire up. This is from our American colleagues. This is that extreme scenario, putting those extra physics in, and this is that low confidence. This is the worst case scenario, and I put in what we call RCP 4.5. This is exceeding Paris, 3-degree warming globally, You can see how much ice sheet we're losing there. If we meet Paris, keep it below 2 degrees, the 2.6 scenario at the top, we save that ice shelf. Even in this worst case scenario model, we save that ice shelf. So that's a positive from this worst case scenario model. So to meet Paris, we essentially have to halve emissions by 2030, and time's ticking. So we have to keep that pressure up to make sure that we are meeting our obligations to do that. So thank you very much, and thank you again for your attention.
Well, tēnā koutou, tēnā koutou, tēnā koutou. My name is Peter Barrett. I grew up on a Waikato farm in the 1940s, discovered caving around Waitomo in the 50s, and then went to Antarctica in the early 60s. And I'm now 84 and a professor of geology, an emeritus professor. And so you'll not be surprised when I say tonight that I'm very proud of my last PhD student, Professor Rob McKay. In Italy, I have to share this pride with Tim Naish, who is currently in Europe. So it's really an honour and a privilege to propose a vote of thanks to Professor Rob for such a thought-provoking and, I'd say, a challenging lecture, but with some moderately good news at the end, perhaps. But I'm sorry, I have to acknowledge Professor Bryony Jones. Also, Marilyn Street, Honourable Marilyn Street, and Rob's wife Jo and family. And it's also great to see so many colleagues of friends of Rob's, but also the wider Wellington community here. So Rob's talk has really, I think, neatly summarised one of the two existential threats of our time. The others being the nuclear threat, now as high as ever. But in this issue of avoiding future climate catastrophe, Rob's made it simple. It's stop emitting greenhouse gases, and especially CO2, because of its millennial lifetime. And so the core of his talk, as we've seen, is how we can use a mix of past records from both ice and strata, and to constrain these models that improve future ice and climate predictions. Now, keeping up with the science is a remarkable achievement. It's 25 years, Rob, since you were a young master's student. I have to confess I haven't kept up, but you have, so thank you. But it does remind me that you started out in Antarctica when we walked 20 kilometres to the edge of the polar plateau to put in a frisbee. It had a serious purpose. It was to collect diatoms that were blowing out of the polar plateau. And it had something to do with that serious debate. But that also reminds me that earlier that season, I was part of a drawing team off the Antarctic coast, Cape Roberts Project, where we were looking at climate between 20 and 30 million years ago. And at that time, a knowledge of past temperature modelling was nothing like it is today. In fact, I was able to fairly represent it by a graph I drew up on the wall of the camp's dining area with, it was actually for a visiting minister, I think he's probably here today, Simon Upton. Temperature falling about 10 degrees over the last 50 million years, but rising 2 degrees over the next 100 years if we did nothing about it. We knew that then, admittedly, not the way we know it now. But both data and modelling have expanded astronomically in their sophistication over the last 25 years, as we've seen through the efforts. A lot of it led by Victoria, but the global science community. And so we can now be much more certain about the future, and we can also see that we haven't done enough about it. Now, Rob and his group, the Antarctica Research Centre, are really world leaders in evidence-based records of research on climate. And the results and consequences, I think, are being very clearly communicated, as we've seen this evening. So this work has to continue so that the world knows what it's facing in the next few years. But most of all, it seems to me that we also need comparable rigour and transparency in our economic systems to make informed decisions about providing for a reduction in greenhouse gas emissions and adapting. Now, we have to leave that to others. Geologists can't do everything. But I'd like for a moment to return to Rob's other qualities as a teacher and a mentor. I've had the privilege of attending his fourth year classes in recent years on paleoclimate. He sets both old and new, but always challenging papers for students to read. But he begins by teaching them how to read and is always patient and supportive. In fact, he's a master in balancing rigour and humanity. So thanks, Rob, for this opportunity to talk a little bit about you and to thank you for a truly motivational lecture and to invite you, the audience, to join with Rob and me in the Hunter Common Room next door for refreshments. But I must first ask you all to show our gratitude to Professor Rob McKay for an outstanding inaugural lecture.